So this is just following on from the irrational pi video, and this is something that we made in the previous video effectively, which was pretty patterns basically, and I might change it from irrational pi to pretty patterns in pi or something else, but it shows the irrationality of of the number pi using Python. And basically we've got this main module over here. We use numpy and import modules, and then we've got our main function over here, and our main function, which is just the main entry point of the code, it just calls this function that we've created, which is irrational pi. And I've actually called it twice, and the reason why we'll see what actually happens in here. But if we just recall, we can put in a number of loops, and it goes in and creates a whole bunch of well, it creates a numpy line space, so which is effectively an array, an ND array, and it starts from 0 and goes up to a certain number of degrees times by the number of loops. And loops is an argument. It defaults to 100, but we can specify other values. And then it's like of size 10,000 over here. Then we just convert that into radians, and then we calculate our complex number from that, which is e to the theta radians times by the square root of -1, and e to the pi times by the theta radians times by the square root of -1. So that's basically all we are doing over there. And then we convert our complex number into its real and its orthogonal parts. So and I did talk about real and orthogonal parts. So this is the real part, and this piece here is the orthogonal part of the number, and the orthogonal part of the number is a number times by the square root of -1. Now we could draw it on the complex plane. I did do this already in the previous video, so I'll just do this quickly. But that's our complex plane over here, and we had our x value over here and our y value over here. That's our normal Cartesian coordinates, and if we do an undo of that, and then we just say it looks exactly the same. We've got this real piece here. These are our real numbers, the numbers that we're used to, and these are our multiples of the square roots of -1, which classically were called imaginary numbers, but we're calling them orthogonal numbers. Over here, orthogonal numbers. So that's pretty much it. Let's get rid of that now. And in that, we then did a little plot. So we created a plot with some very specific settings there. We had a white line, black background, equal aspect ratio. We removed our grid lines, and we made the x and y limits to go between -2.5 horizontally and both vertically. Now the extra piece that I've added in, and this is the nice thing about doing everything inside of functions here, so creating a function like that and then having a main function that calls our function, is that I can do this little change, and I create a path here, and that's just the path to save. This is where the folder actually exists. So like I could have done a copy path, which is exactly what I did. I did a copy path, but this folder, this file lives in this particular folder. We can actually see it in the breadcrumbs, I think, if I hover over it. Does it show you? It shows the entire path there in the breadcrumbs. I can't hover over the last piece, but we can see it popping up there. And inside that, I've actually got an assets folder. In the assets folder, if I pull it up wherever it does exist there, assets folder, it looks like this. And at the moment, I haven't done anything. So this part of the video is going to be completely live. I've not actually run this yet. So I'm hoping that this plot.savefig, so I've commented out the plot.show. So instead of showing two plots, I'm going to do plot.savefig. And we'll see what actually comes about. And I've just run this function. I'm just going to run it the one time just to start there, and hit F5 and just see if it does create a figure there. So it's running, it's doing its thing. And it looks like it's completed. And I was hoping to see a figure go in here somewhere, but I haven't yet. So maybe if I hit the refresh button. And this is why we do these things live, because it's more fun that way, because things break or they don't go. So we've saved the figure, but it hasn't saved it anywhere in particular, so now I have to go and find out why. And I actually realise why, which is that I forgot to put the / over here, and which is the actual end of the folder. So now what I can do is the full path like that, and it's going to be equal to, and then the full path will be, if I take this whole F string out here, so I'll X that out and paste it over here, our full path is going to be the path in the chart. And the reason why I do that is that I can then do a print and then file saved here, and then comma full path like that, and we can pass this full path now into the save fig. And I'll just comment that out for a second just to make sure that runs, but it will be missing this /. So if I run this now, it's not going to actually do the saving of the figure at this point in time. But there we go, we can see that it would be saved here, which is this, or it would be saved here, which is the assets chart. And if I do go to the actual folder, that means that, oops, I've just maximized on that. If I do go to the folder and I go up one level, I presume I will have a chart somewhere in here. There we go, that's our assets chart, and it did actually go there, so it went into the wrong place. So I'm going to remove it from here just by hitting the delete. That should have removed it, that's fine. And I will double click back in here just to go back to the assets folder, and we should be able to, we will get that in there. So now we know that's going to be successful. So, but the thing that we're going to do is actually, and this is the nice part about it, but we'll start with just 2 of them maybe. I'm tempted to do more because we can do as many as we'll start with 2 just to see what that looks like. So we're running our little piece of code. I might actually even put a time function on it. So let's put an import of time, the time module, just to see how long this function actually takes to run. And then we can do something like t0 equals time dot time, like that. And at the end of the function over here, we've got it. Interestingly, I guess I want to sort of like split it out and see which time the various different pieces, but this is all of the actual computation parts. So t1 equals time. There's many ways of doing this. Dot time. I always like this because it's fast. So that's sort of like the crunching time, and then we've got our plotting time and our actual saving time as well. But I'll encompass them all in one, I guess. So, I could just do the plot here, I guess. So we haven't got a plot.show anymore, but t2 equals time dot time, like that. And then just before we do the saving thing, or just after, in fact, we can do it, which is print, and then computing time, which is going to be, I think if I put this into an F string, if I remember how to do this properly, so the computing time is going to be t1 minus t0, and then dot 2f. I think that's the 2 decimal places, like that. Copy that, and our other one, which is t2 to t1. I could put them in brackets to be unambiguous about it. I think that should be fine anyway. And that's the 2 decimal places. And so one's our computing time and one's our plotting time. So just sort of like seeing how long it is. The actual thing, what I should really have a T3 because saving the figure is probably going to be the biggest cost of all. But let's just, I think, well, I have actually run it anyway, but maybe I'll run it a second time just to, so I know that it's run because I had a little glance across, and these are the two charts that I produced. So that's our first chart, and that is our second chart. And notice they're completely different, and I only made a one value difference between both of them in the top of the code over here. So when what we've called our, where is it over here, loops, what we've called our loops over here, which is the argument that goes in here. So instead of, so we had 10,000 loops, and then we had 10,001 loops, and it created, like, you know, completely different spiral patterns. So I'm just going to run the exact same code again, and really that's to check that it's not going to prompt for an overwrite of the files, as in because the files already exists. So we can see, like, it's kind of like running there, and actually we can see it running. And if we just go and open up the terminal a little bit more, just have a little inspection of what came out of there, you see the computing time's immediately fast, and the plotting time takes half a second there, and the plotting time the second time around, we had a cost saving, so it took 0.15 of a second. And I imagine that if I did do, so maybe I will do a T3, finally I probably should do it, but basically T3 equals time dot time, like that, and then we can sort of like, we can just say that this is going to be T3 minus T2. We can see the cost of how long it takes to save, and I'm using Google Drive here, so file save time, so it's our file save time. And that's fine, we'll see all of that pop up in our thing. And so for each one of these, we'll get a, for each one of these, we're going to get 3 lines of times over here, telling us like how long each thing's cost. But the computational time in Python's super fast actually. Python's known as a slow language, but it's relative. When you're using NumPy, it's extremely fast. But the plotting aspect of it was slower, and without a shadow of a doubt, saving to a Google Drive cloud thing is going to be the slowest component of all. So let's just continue there anyway, and we can do something like, I could put a little for loop there for I in range, and maybe we'll do like, we could do 100 charts quite fast, but let's just do 0 to 100,000. 100,000, but we'll do it in increments of, I don't know, 1,000. So, and here we are just going to pass it in. So I will be in the loop now, and we can move this past, we can tap this into the for loop like that, and we can remove that. Now that's going to do 100 different charts. It's going to create 100 charts in this little screen over here. I wonder if that's too much. Maybe we'll make our increment sizes 100, then we'll only get 10. Is 100 too much? Probably, but if I multiply that by 2, that will be 50 charts then, and if I multiply that by another 2, that will be 25 charts, so bunches of 4,000. Basically what I did in my head there was, hopefully if my calculations are right, 123 divided by 4,000, just to make sure that the numbers are correct. We can get 25 charts in our little assets folder. So I'm just going to run that now, because that should all run, and I might even scroll up a little bit. We'll see this as it actually runs. So it's initiating now. Funnily enough, there's a long time taken just to initiate, which is interesting. We see, I'm hoping that the computing time is correct, but anyway, we can see all of our files being saved, and it's saving them with the numbers as well. But on each one, we can see it's scrolling quite fast, but the saving time is the massive cost. It's like, The computing time is 0 seconds, the plotting time is 0.19 of a second, and the saving time tends to be, looks like it's about a second to save each time. So, and you can actually see these going along there. We can see it populating piece by piece. There we go, it's saving them as it's running. So we're getting 25 charts. That one looks like an interesting one. It's done a really nice, cute little pattern there. And of course I started with 0, so that was a faux pas. Shouldn't have done that one. I started with a complete blank screen, but we've got 25 charts here and we can scroll through them relatively quickly. We can sort of like see the overview picture, although some of them just look like big fat circles anyway. I wonder if I can change the display. Well, that's our chart with 0 loops, so that's just going to be a big blank picture. Let's just see if we can run it like that and see how quick it is. I wonder if I make the screen a little bit smaller as well. Zoom down on our screen size just to save the intensity of it, and then just run through. So that's with our 4,000 here, so we've got 4,000 loops. That's with 8,000 loops. And just notice the difference, 4,000, 8,000. That's 10,000 loops. That's 10,000. That was our 10,000 and our 10,001, so they've fallen in there. That's is that 120? That's 10,000. Is that 12,000? Yeah, that's 12,000 there. So 16,000. So it's nearly like it's creating snowflakes. Maybe Pi's got something to do with snowflakes as well. On this particular one, I'm not sure if it will come out on the screen, but we can see that there's actually like tiny little black dots that are sporadically put inside of there. So inside of our main circle, and continue and continue. And again, like we've got these like little patterns that occur inside of the bigger pattern, but none of these are the same. That's a very nice one, by the way. So that's 32,000 loops. What's that one? 36,000 loops. So that one's really pretty. Yeah, they look like doilies as well. So this one here is 44,000 loops. Is there anything to do with the 44? Does it create something that's slightly different? But you know, that's looking very different there anyway. And we can keep going on. 52,000 loops. Every one of them's extremely different. Again, 60,000's got this interesting pattern on it. 64, 68,000 over there. A nice recurring pattern again. 72,000, 80,000 loops there. So quite interesting. And it actually does it did it pretty fast, by the way. So, and this is all about pi being a rational number. The other stuff was dark physics that had nothing to do with it. So yeah, that was our, so that's all like being dumped into the assets folder, and we can play around with that and do a multitude of different things. And I'm just going to check because it's a bit scary, or not scary, but like maybe a sign. But the computing time is 0.0, but it might be because I've rounded it down. So just going to have a look just to make sure that I've done the computation right on that. T0 equals time dot time and T1 equals time dot time. Yeah, that's perfectly fine. And this is all of the stuff that goes in the interluding period, which is creating this line space. So this creating this return evenly spaced numbers over a specified interval. So we specified our interval, naught and however many loops you've got, and evenly spaced numbers in there. So every 10,000, I guess it was. And then we converted the degrees into radians. So that was, so this just converted this entire array into a new array over here. And then we did our computation for our complex number, effectively e to the number of radians, so e to the I radians, and then e to the I pi radians over here. And then we split out our real and orthogonal numbers, and we did all of this between T0 and T1, and it didn't even take 0.01 of a second. Now, I guess if we did to 3 decimal places, maybe we would have seen something. I might actually do that for the next one. So I'll do that one too. Our computing time needs to be a bit more significant in figures. There we go, we'll throw in an extra decimal place. Maybe we'll get a 0.001. So, and that's pretty much it. But like, yeah, when we do look down here, there's no surprise really, but yeah, massive time there. That took 2 seconds, that took 2.5 seconds, that took 1 second. So our plotting time takes typically 1/4 of a second. Remember on our first run, the first one took 1/2 second, but it looks like something's cached in the memory. But generally speaking, the plotting time takes 1/4 of a second, and the file saving time takes 1 or 2 seconds by the looks of it. I got some kind of warning here as well. What was this warning? Runtime warning. More than 20 figures have been opened. Okay. Figures created through PyPlot interface are retained until explicitly closed and may consume too much memory. To control this warning, see fix max open warning. Maybe I should close the figure size some way. So I might actually do this, which is I've got something open already here. After saving the fig in matplotlib, can I remove the, and I'm going to just see what the actual error was, because I'm going to try and remove that if I can. I think it's just called can I remove the fig from memory? Question mark. I'll hit return on that and possibly do a zoom in, Control++ a few times so you can see the question that was asked there. I think, okay, just the plot.close. Remove the figure from memory, fig.clf plot.close. Okay, so that should be good enough. So and I think that might just be sufficient actually, because we're not using actual figure there. I wonder if I could do a plt.clf when it's clear the current figure. That might be sufficient. And this one here, if I hover over it, close a figure window, but I don't actually have a figure window open. So if I just hover back here, I shouldn't really be using a large language model to give me answers, but I do. To clear the figure contents, this clears the axis and all the artists on the figure. The plot.close is going to close the actual figure. To close the figure, this will detach it from the graphical user. Delete figure. To dereference it, this allows the memory to be freed up. So, but the thing about it is, I just do a plot dot. I wonder if I don't know if you can do a delete dot plot. Because I do this thing here, this little piece of code, it's got a fig and ax dot plot. Is plot dot close sufficient to clear the memory? Question mark. Just ask that one as a side. And while it's answering, I'm just going to go back here. Consider using matplotlib.pyplot.close. Okay, so actually the answer's here, which is going to be a better answer. It'll be interesting to see what this answers back. So, no, just plotting plot.close is not sufficiently to fully clear the matplotlib figure from the memory. Plot.close function closes the figure window, but does not delete the figure object itself. The figure still exists, but I don't have a figure there. in the internal state of matplotlib, maintains references to plotted data, blah, blah, blah. I think that that will be sufficient because we haven't created figures in the way that we're doing it, and so that sometimes the large language models do lead you down the wrong avenue. So just as consider using matplotlib.pyplot.close. So that should be sufficient there. So if I was to run it again, hopefully that won't pop up after 20 chart plots. So that's pretty much it. We got 20 nice charts. Maybe I will run it again, and this time actually I will create more loops here. But this time, if I go from 1 to 100,000, maybe I'll have to increase this to 100,001 just to be on the safe side. I don't know if you do or don't. But at least we won't have a blank first one, and we'll also get another 20 set of numbers, because each one now is going to be, rather than going 0 to 4,000 to 8,000, we're going to go from 1 to 4,001 to 8,001, and we'd actually be able to see the 1 differences each time, which was the piece that was actually quite interesting. So what I'm going to do is, we can see this running sort of like live. If I go back to our view, that looks like that. So I just clicked on it to get that view. And then I'm going to run it, and I'll pull it in on the screen at the same time so we can see it running. So I'm going to hit F5 to run it. I've got a couple of little changes that are going to go there, and it's beginning to fire up. This will slow things down a tiny bit, I imagine, because we're going to see our charts pop up. Note that chart 1 is still blank, but there might be something on it. But what will be interesting is if we look at chart 4001, for example, which is over here, and compare it to chart 4000, which is over there, they are just completely different. 4000 is this chart here, and 4001 is that chart there. And also we can see that now it's taking, we can see the computing time is taking 0.001 of a second. So there wasn't actually an error in the calculation. It was just rounded off to 2 decimal places. So the computing time is extremely fast, but the actual file saving time is still there. We didn't throw us any error messages, and I think we're towards, yeah, we've created all of the charts, and we've had no error messages as far as I can see there. So yeah, so that's where we run it, and 4,000, 8,000, so forth. Interesting. That was the bit piece before. Why don't I see all of them? 4001, 8001. But it's got 12 years, 12,001. It just hovers over to the next line. I'll have to do a control minus to get it so that we can see all of the text and the code. So it ran everything in the same way. And we can now go through. I wonder what our chart 1 is, because that should be one line somewhere. Oh, we do get something. So that's our 1 revolution, and that's what it initially looks like. It spirals round and round and round and round, and it ends there. And notice how they just don't overlap. So that's kind of like the key piece of it. And maybe if I did a 2 and a 3 and a 4, so you know, that could be like the next thing. We'd see it organically grow. And this is our, that was our 4,000 point, was it? That's our 4001. So notice 4,000, but the minute we do our loops, and we only change our loop over here by, like literally from, so our loops here was 4,000, and from 4,000 to 4001 are completely different images. So that's our 4,000, that's our 4001. And likewise, that's our 8,000. And let's just see what our 8,001 is. They're much more similar. That's our 10,000. That's our 10,001. They were very different, but we knew that from before. That's our 12,000. That's our 12,001. So just changing by 1 loop. So we can see that there's a massive, I'm going to call it nearly chaotic. So there's chaos in there, as in it's unpredictable. Like this small change in the integer value has a dramatic change in the actual shape of the spiral that's created. So 16,000 to 16,001, that's a nice interesting one because we've got three little black dots in the center over there. So it's quite an interesting one. That's our 20,000 and that's our 20,001. This is our 24,000 and 24,001. So again, that's that pair. It's 28,000 to 1. Slight difference if that shows up on the video. It's 32,000. So they were like dotty little things in the middle. That's our 36,000. Again, we can see the difference between them. 40,000 and 40,001. They're both very different. That's our 44,000, which was completely different, and our 44,001. So again, very different. And we can keep on going on. So this is our 60,000 and 60,001. So again, like huge differences. That's a nice, interesting one. Again, 64,000 is white with tiny little dots in there from here and there, but then we get this like little pattern right in the middle over there that's repeated. So again, 68,000 to 68,001, big difference between them. Oh, that's a nice one. 72,000 and 72,001. So a pattern that we haven't seen before, emerging, like vastly different from everything else. And it keeps going on. 92,000, 96,000, 96,001, and that's the end of it. So that's pretty much it. We've now got this into a nice format. We can do a whole lot more. Now we're saving our files. We were able to save our files just by allocating a path like this, and then just doing a save figure rather than a plot.show, and we were able to loop through using our for loop here and putting numbers in. We could do a whole variety or host of numbers and see what it's like. So that's basically it. That's our second irrational pi in Python. If you like this video, hit the like button, the thumbs up button, the follow button, share it with friends, share it with everyone else. And even if you don't like it, still hit the thumbs up button, the like button and the follow button. Stop recording.